Welcome back, ladies and gentlemen. In this video, we're going to be checking out how to draw diagrams of circuits. We're going to focus just on simple circuits for now, but we're going to be able to apply these skills to more complicated circuits and later on as we go. We're also going to check out how we can, a couple examples of how we can apply Ohm's law and the idea of electric power when we analyze a circuit. And we're going to wrap this one up by looking at these things called DMMs, or digital multimeters. They also go by various other names. They're going to allow you to measure certain properties of an electric circuit. Alright, so starting out, what are we going to do to diagram a circuit and keep it simple? So we could have a battery, for example, and one bumpy end, and the bumpy end is usually the positive end. You have a negative end of a battery, right? And you might connect the battery to some sort of light bulb. The light bulb might be sitting in some sort of base. That, right? And there's some sort of switch. How would I draw a switch? Well, maybe a switch looks a little like this. And you've got the actual switch sticking out of it. So we have to connect these different components here. And so we're going to have a wire going to the light bulb, and inside the light bulb you got some interesting stuff going on. There are some small wires, and the filament inside that glows, gives off the light. It's an old style called an incandescent light. Easy to draw. Okay, but the wire comes out of that guy. We've got to go to the switch, and we've got to connect back to the battery. Well, this is not a proper circuit diagram. It takes a little bit longer to draw this, and sometimes these are easy, simple components. Sometimes the components are kind of complicated, and you don't want to have to draw them out. So we're going to replace these images right here with some standardized types of things. For example, the symbols. So we got the device or the component. Let's make a quick list here. And we're going to have the symbol. And so first let's talk about a battery. Okay. The symbol for a battery, according to your textbook, is going to be something like this. You have a longer line and a shorter line. Some books also do double of that. Either one is acceptable. I will usually choose this one. It's just a little faster to draw, but either one is fine. When you draw this particular symbol, the end with the longer line is your positive end, and the end with the shorter line is your negative end. Same thing here. There's your positive, and there's your negative. And that will absolutely matter. So then, what else are we going to have? We have the light bulb itself. So instead of just focusing on a light bulb, let's focus on anything that's going to use the energy provided by the electricity here. So anything that's using that energy, we'll call it a resistor. And the resistor has a certain symbol that we want to use. Squiggly line, like that. And we can rotate it. We can draw it this way, or whatever we need to do. But that's a resistor. And remember, the resistor could be a light, could be a motor, etc. Anything like that. What else do we have? We have a switch, right? Now, in the diagrams that I draw, and the ones I'm going to ask you to make, I'm not going to ask you to draw switches, really. Although it is really simple. You simply have a wire coming in, a wire going out, and all you do is that. That is a symbol for a switch, where the connection is broken right here, so the switch is in the off position when it's drawn like this. To put it in the on position, what you do is you draw it kind of just like there, just offset but touching, right? It's a very subtle thing. I'm not concerned with switches. I'm not going to ask you to draw them most of the time, but at least you know what it is, right? And so now what? We have, the wires, the connecting wires. That's super easy. Just draw lines. The lines are usually drawn straight for the wires. Usually not curvy, kind of like I did here. So let's look at an example. What would this turn into using these symbols. Okay, and I'm also going to have to add some labels, right? So check this out. I'll probably be able to fit it in here. I want to start with the battery, and so long line, short line, and I have some wires coming out of the battery, right? So wire connecting here, up, and I'm going to turn, and the first thing I get to is I'm going to get to the light bulb, which is acting as a resistor. Right? And then I have a switch over here. So I'm going to draw my switch up and then keep the wire going. And there we go. And so you can see a few things happening, right? Some labels. This is a battery. And oops, come on, marker. There we go. Battery right there. We have a positive side and a negative side to the battery. We have a switch. Easy to see here. We have our light bulb. Which is basically just a resistor. There. Okay, now what else is going on? We have wires, obviously. Wires here. Make the line. There we go. Wires connecting everything together. Okay, and what else is going on? Well, okay, so what's going to happen when we close the switch? Right now the switch is open, right? So we have an open circuit. It will not work. So it's in the off position. Well, if we were to close it, let me use a different color here. Let me set this apart just a bit. So we're going to close that switch. So from there, we're touching, right? And so now we're going to get the light bulb to turn on. So now the switch is closed. We have this closed circuit, this complete pathway. And so the current, which way is the current going to flow? Right, so let me draw some arrows for the current. Let me go skinny marker, not the black one. Let me go the blue. I'll show the current with the blue. Current will flow out of the positive end of the battery, through the wires, this, and through the switch, and back to the battery. So the current, remember what current is. Current is charges that are moving. Current is a capital I, right? So the charges are moving. So the charges leave the battery, go through everything, and come back to the battery. Charges are not used up. Super important. It's a kind of a common misconception. The charges are not used up. They're not. But what's interesting is this. I mean, think about the wires. What is actually moving? The charges that are moving, well, they have to be either the positives or the negatives. What's more easily made to move? The protons, which are positive, and the protons are in the nuclei of all the atoms, or the electrons, which are negative. It's the electrons. So electrons are made to move. So here's the problem, and I should have described this already. Here's the issue. Really what's going on is it is electrons flowing in the wire, but they're not doing this. The electrons actually are sort of repelled by the negative terminal of the battery. Electrons will flow away from the negative side and out, and they'll flow this way and this way. This is actually what's going on. This is the reality, electron flow. But nobody ever uses that. The convention is to talk about the flow of positive charges, conventional current. That is what we will use. And I won't say conventional all the time. I'll just call it current. But we're going to talk about positive charges moving, and here's the thing. It's equivalent in the effect that it has. There's no difference in the result that you get. The light bulb still lights up when you talk about conventional current instead of talking about electron flow. So we are going to focus on conventional current, absolutely. I'm going to stop talking about electrons and electron flow when we're dealing with circuits. I do not want anyone to get confused. All right, so Now, what I'd like to do for a moment is go back to a previous idea. The waterfall. So, you remember that. Well, it's an awesome analogy. And recall what we had. Let me go with this guy. We had some lake. That was Upper Lake, and then water found its way out of Upper Lake, and it was made to fall down the waterfall, and crashing at the bottom, all kinds of foamy stuff happening. And this marker just doesn't want to work. There we go. And water flowed over the waterfall into Lower Lake. Okay. And from Lower Lake, what we had to do to keep it going forever was we had to pump the water out. From Lower Lake and pump it back up into Upper Lake. And so what did we see? Well, okay. Waterfall, went down, foamy stuff. And we saw water being pumped back up into Upper Lake and falling back down the waterfall all over again and going on forever. So we had this pump. And why bother doing this in the first place? Well, what we were saying was, with this water wheel we set up here, that the water wheel could turn something mechanical and make something happen for us, or it could turn a generator and make electricity for us, anything we wanted, right? So we said all these things. We basically got energy out here, and at the pump we had to put energy in. Okay, so we're not getting energy for free. It's not perpetual motion or anything like that. Conservation of energy still applies as well. Now, when I draw a circuit, though, I like to draw the diagram to always show what we call the voltage gain, which is like your battery and so on one side, and all of the voltage drops on the other. So check this out. Your voltage gain is like your charge pump, that's your battery. Your voltage drop is anything using the energy in the circuit, so that's like your resistor. And I like to put them on either side of the circuit. So I will usually draw my voltage source on one side. I will usually draw the wires going up, over, I'll go down, squiggly line for the resistor, wires down and back to my voltage source. And a couple labels are helpful. So I have positive here, negative there. This is a resistor. I'll label it capital R. And remember, the resistor itself, that could be a motor, that could be a light, that could be a speaker, that could be a heater, anything using the electric energy here that the voltage source puts into the circuit. This thing takes it out. I should also show the direction of the current, at least a bit. It's like that, so I can put a capital I there for current. Awesome. So, and remember, this is conventional current, but we can just say current. So I like to draw the voltage gain on one side and the voltage drop on the other side. So those terms, voltage gain and voltage drop, they're worth using, or you could say voltage gain. You could say voltage source. I guess you could say charge pump, although that's a little odd, a little unusual, but that's kind of what it is if you think about it. Over here, you could say resistor. That's the most common. You could say voltage drop. You'll hear me use that, voltage drop. Maybe some other stuff you can use there too. But think about why use the terms voltage gain or voltage drop? Well, it kind of comes back to the waterfall analogy. When we're pumping the water to Upper Lake, we're gaining in energy in the water. We're adding energy to the water. And when it's falling down the waterfall, the water literally is dropping. It's losing that energy. Now it's gaining kinetic energy, sure, but it's losing the potential energy that it had. Well, the same thing sort of happens in a circuit. The voltage source produces a gain in the charges, and the resistor produces a voltage drop in those charges. So this is kind of interesting. So we'll see sort of a high side before the resistor and a low side after the resistor, just like we do here, Upper Lake and Lower Lake. And the upper and lower lakes, they are not important for the functioning of this thing. They just help connect everything together, right? Well, these wires, they're not terribly important for the functioning of the circuit, but they connect things. That'll be helpful to understand. Make sure you remember that. Now, what about applying Ohm's law to this? Okay, let's see what happens. So, Ohm's law. Ohm's law is the relationship between voltage, current, and resistance. And basically we all know it as V equals IR. You know how I like to see it, but that's fine. Either way. This is going to be voltage divided by resistance. Okay. What if we have some information about this circuit now? Let's say our voltage gain from the battery, let's make it 12 volts. Equal to 12 volts. And let's say our resistor, I'll write it up here so there's room, resistor is equal to 110 ohms. Remember the symbol for ohms is like an upside down horseshoe almost. It's a Greek letter omega, capital omega. Now, with those two bits of information, we can find the current that will flow through the circuit. We can solve for I, not a problem, right? So that's what I'm going to do. So I'll just do it right from here. So I know voltage divided by resistance. I have 12 volts. And I have resistance of 110 ohms. Sorry, it looks like an R a little bit. That's going to happen. This comes out to 0.109 amps. Amperes is the unit for electric current, right? So I just used Ohm's law to find the current in this circuit. So I could label that 109 amps. Cool. Well, a couple questions about this. What happens to current if we double the voltage? So what happens to current I if we double the voltage V? There's our question. Well, let's check that out. Here we go. We know that I is still equal to voltage divided by resistance, but we're going to double the voltage. So 2 times my 12 volts. I'm doubling that voltage. That just means I'm keeping the resistance the same, 110 ohms. And so, what's the current? Well, I'm essentially taking this right here and multiplying that by 2. And so I essentially have to do the same to the other side of the equal sign to keep the equation balanced. So I will have 2 times the original current. Well, the original current is this guy, so I'll have 2 times the original current, 0.109 amps. And so my new current is going to be twice as much, 0.218 amps. Twice, double the voltage, double the current. Okay. Double the voltage. Double the trouble, the current. That's kind of important to remember. But what happens if we double the resistance and keep the voltage the same? So let's check that out. What happens to current if we double resistance? New question. So, and we're going to keep the voltage the same as it was originally, so voltage will still be 12 volts. Okay, so well, I still have the same relationship, and I'm going to have the same 12 volts, but now I'm going to double the resistance. So 2 times 110 ohms. Well, look at that. The 2 is now in the denominator, so the whole thing gets smaller. I'm essentially multiplying by 1/2, right? And so that's going to be multiplying by 1/2 by the original sort of answer. Remember, the original answer was 12 divided by 110. Well, I've got my 12 divided by 110 right there. And then I'm having to multiply by 1/2. So the 12 divided by, divided by 110 is my 0.109 amps. And so I need half of that. So my current is going to be pretty small here, 0.0545 amps. Double the resistance. This is really where you're doubling the trouble. We're not doubling the current, are we? Ooh. We're going to have half the resistance. So you get half the resistance. What's the past tense verb form of that word, halved? This is where you're smarter than me. Halved? Question mark, I think. Halve the current. You know what I mean. That's also important to realize. Double the resistance, current is cut in half. Double the voltage, current is doubled. And that all comes from Ohm's law. Right here. Awesome. Some interesting questions coming next, however. And so we have to address this. Well, let's look at the same circuit. Let me redraw it so I don't have to keep going to that page. So that circuit was essentially a battery, a resistor, squiggly. Notice how quickly that diagram goes together. The voltage was originally 12 volts. The resistance was originally 110 ohms. Okay. And originally the current was 0.109 amps. All right, so now let's analyze the power used by the circuit. Well, power is equal to current times voltage, and I have the current, I have the voltage. That's kind of handy. So 0.109 amps is my current. My voltage is 12 volts. So the power in this circuit, or the power used by the circuit, I get 1.308 watts. Remember, power is measured in watts, capital W. There we go. So, box, around the answer. Boom, it's good. Now, we just completed a couple sort of what-if kind of questions, though, right? We said, what happens to the current if we double the voltage? We doubled the voltage. What happens to current if we double the resistance? We doubled the resistance. What happens here to the power? So what happens if, there's the question, what happens to power if voltage is doubled and also if resistance is doubled? We're going to answer two different questions here. What happens to power if voltage is doubled, and what happens to power if resistance is doubled? Okay, so check this out. Let's answer the first one first. Let's go in order. Voltage. If we double the voltage, we get 12 volts. 12 times 2 is, we get 24 volts, I'm sorry. But remember, when we doubled the voltage, that also changed the current. And current is part of this equation also. Okay, so I've got to rewrite that. So if we have 2 times the voltage, we're going to answer that. So the power is now going to be, my voltage is 2 times 12 volts. I'm doubling that. But when I did that, I got twice the current. I got double the current also. So I got twice my 0.109 amps. Look at what's going on here. The original was basically 0.109 times 12. I have my 0.109. I have my times 12. But I got a times 2 and a times 2. That's like a times 4. So 4 times the original 0.109 times 12. 4 times the original 0.109 times 12. So what we get, oh, handy dandy calculator, right? Oops, don't drop your calculators. It's not conducive to their functioning. 9 times 12 times 4. Okay. We get 5.232 watts. This is 4 times the original amount of power. All we did was we doubled the voltage. But in doubling the voltage, it doubled the current also, which led to 4 times the amount of power being used by this circuit. Wow. So double the voltage leads to double the current, therefore 4 times the power. Wow. Okay. Is the same thing going to happen when we mess around with the resistance? Let's find out. So now we're going to answer the second question here. If we double the resistance, what's going on? So 2 times resistance. Let's look at that. And well, when we doubled the resistance, did the voltage change? No, we still had 12 volts. And doubling the resistance, we found, gave us half the amount of current. Voltage was the same, but we got half the amount of current. Okay, so let's set up our equation for power in this circuit. Voltage is the same, 12 volts, but we got half the amount of current, so 1/2 times the 0.109 amps times the same voltage, 12 volts. That's unchanged. So what do we get here? Well, that's 5 times. Sorry. Come on, calculator. I shouldn't have dropped you. I'm so sorry. Please work for me. Times 0.109 times 12. My calculator decided to work for me. It was nice. Okay, so we see the power now. Since we doubled the resistance, the power used by the circuit, compare this value to the original answer, looks like it's 1/2 the original answer. So, doubling the resistance leads to 1/2 the power used by that circuit. That was an easier thing to realize. Here, there was this extra step. Doubling the voltage had this initial effect of doubling the current, and both of those led to more power, 4 times more power. Interesting stuff going on here. Okay, so we've looked at Ohm's law, we've looked at electric power in this circuit, and we've seen some cool stuff.